All right, we can probably get started. Welcome everybody to the last day of the evening sessions of the Rubin Virtual Data Academy 2024. And today we're going to cover more than anything else stuff having to do with time domain, but also there will be a little bit about source injection. Again, since the evening sessions only take place 3 times during the Academy, we chose 2 probably more advanced but important tutorials for those of you who do not have a chance to watch everything. So I'm going to basically put the resource list on this together with the link to the Slack channel on the Slack it's not Slack channel on the chat window. So let me copy this into chat window, and you will be able to get the resources there. But I suspect that at this point, most of you probably participated yesterday, so you already have it. If you have any questions, please either raise your hand or maybe send a note in a chat, which certainly can respond to that. Again, we're going to work with data.lssc.cloud, but today we're going to have one tutorial that actually is already online. That's the one that I believe Douglas will be presenting first, and then the second one you will have to actually do something a little different than usual. So this is the agenda for today's session. Douglas will be presenting the tutorial from DP 0.2, Notebook 5, and will be about source detection. And there is some new stuff in that by comparison to what you might have seen months ago, because now it has an image display using Firefly. And then Jeff Carlin will present a second second part of the tutorials today, or the presentations today, and there will be a custom contributed notebook which was presented earlier this morning and was prepared by Vincenzo Petrecca, and it's about how to extract a light curve from variable star, but also supernova. Those are relatively long tutorials, so we are going to go for 1.5 hours, and only then we're going to take a break. And in addition to that, I would like for all of you to fill the exit poll for the Academy. The feedback is very, very important to us, and you already have the link to the slides, but I'm planning to send an email message to all of you after we're done with the Academy to remind you about that. That particular exit poll is something that allows us to improve the quality and the content of the Rubin Data Academy in the future. So we would love to hear, and please don't hesitate being critical. If you didn't like something, we certainly are all ears for that. So I'm just trying to think what else besides this issue of cloning today's demonstration notebook that you will see being presented by Jeff during the second part. It's the name of the file name is 0.7c lightcurves.ipynb, and again you have all the information about how to get it. There is one issue that I think you have to be careful, and maybe either Doug or Jeff can speak to this, that you have to go into a separate directory, because the directory where all the other notebooks are present is protected from being overwritten. Is that right? Yeah, I think Douglas is nodding his head. So maybe...
Yes, that's correct. That's the standard notebooks directory where your tutorial notebooks is read only. So if you try to do a git clone in that directory, you'll get a permissions problem.
That's right. So hopefully Jeff will remind you to do that. For the breakout sessions, we're going to have those 2. We will not have huge amount of time, but I thought that today maybe the breakout sessions would be best if they're if I stay in the main room answering any basic questions, but maybe Jeff and Douglas will be able to go to breakout rooms and maybe expand on answer questions that maybe need to be expanded upon on the regarding their presentations. Okay, I might be missing something, but I'm not 100% certain. I think that that's pretty much everything, and this is the agenda for today. All right. Okay, so at this point, let me stop sharing, and I'll hand it over to Douglas. So let me just stop sharing here. Great. Okay.
Okay, well, thank you. Let me start sharing my screen. Okay.
There's something weird for some strange okay, perfect.
And let me get the chat window up so I can see that. And oops. Okay. Okay, so I'm starting from the main page, and I'll stick that in the chat window. The main RSP page, the main Rubin Science Platform page. And here I've not even logged in yet. So I will log in. And I'm at Fermi National Accelerator Laboratory. So I'll log in through my provider. I'm logged in. So we'll go to the notebooks aspect. So we'll click on notebooks. And I suggest using a medium-sized server and the recommended kernel image, and then start. And that will take a couple seconds to start up. And the notebook that we'll be looking at will be on source injection, or not, sorry, it'll be on not source injection, but it'll be on let's see, let me pop this up for a second. Okay. Let's see. I usually, although probably not necessary at this point, but I usually open up a terminal window. And okay, my home directory is pretty messy, but we want to go to the notebooks directory and double click on that. And you want to go to your tutorial tutorial notebooks subdirectory in there. And we are going to we'll go to this DP02_05. Well, okay. It's, source detection and measurement notebook. So you'll double click there, and I'm going to make this small. And in fact, I'm going to close this thing because we're going to need a wide area here so to show things properly. So I'm going to close that. So we just have this window open at the moment. You don't have to do that, but for me, I want to so people can watch and see everything all on one screen. I'm doing that. So we are doing source detection and measurement. Now, Rubin pipelines are ready for detection and measurement, but you may wish to adjust the parameters and maybe look at things, try to things. So that standard source detection is at the 5 sigma level. You might want to try to go a little bit lower, or you may try to want to play around with the source detection parameters for some particular reason. And so this notebook, as we see in the introduction, provides a brief introduction to the LSST science pipelines, their source detection, their deblending, and measurement tasks. Now, I won't go into much depth about optimizing these tasks for different types of sources like stars or point sources versus galaxies, but it does give you a general idea of how to run this yourself if you so wish to do so, and also cover how to access the footprint of a detected object and how to do force photometry at user-specified coordinates. So we will do the usual importing packages. So I mean, we get like NumPy, Matplotlib, the various science pipelines, the Butler interface. One thing that we have, and we've seen many of these before, maybe not all of them, but many of these before. The ones that are kind of new here that we haven't really looked at before are these tasks for characterizing the image, source detection, source deblending, making measurements from a single frame, and doing force measurements. So why don't we go ahead and you recall when running a cell in a notebook, you do Shift Enter or Shift Return. And okay, it's taking a few seconds to run. We also will use the AFW display, and we'll use Firefly as the backend. Before we were often using Matplotlib. Firefly is another way of doing looking at images. So we'll set up the display and we'll create a frame, and it pops up this. And this should look familiar for those who've done the portal tutorial, because it's basically the same format as what the portal uses. Now here, what we want to do, we want to be able to look at both the notebook and Firefly simultaneously. So what we do is you get your mouse and you grab this tag and you move it like so, and that way you can see them side by side. So everyone's okay with that? No questions so far? Okay, let's move along. Let's see. We'll do a couple other things just to set things up. We'll set the plot style to be colorblind friendly, and then we will access the butler. We'll instantiate a butler to access the DP02 data set, and in particular the 2.2i/runs/dp0.2 collection. And you've seen that before in previous notebooks when accessing the butler. And recall, the butler is a way of accessing data in data stores, so you don't actually know like the file format or where it is. It's used to kind of hide underneath all that underneath in case things change over time, but you can always access things the same way. Okay, so the first thing we want to do is we want to grab a single visit of processed visit image, or a CalEXP or CalUps. That's the single image, single epoch image. And to do that, we need to define the data ID, which for a CalEXP at the minimum thing to identify a particular CalEXP is the visit number and the detector number. So we will use, this was decided beforehand to use visit 512055 and detector 75. Recalling that the LSST camera has 189 detectors altogether. So we define the data ID, and then we request the butler to get the CalEXP image or the image set according to this data ID. So we do that. Now, this CalEXP includes not only the image itself, but other planes. There's a mask image plane, there's a variance plane, and likewise. We won't go into too much detail here, but if you want to, you can uncomment each of these out, and you can see a little bit more about these. But we will kind of we'll kind of skip over that for the moment. We'll also note that also associated with each CalEXP is a PSF, a point spread function and a WCS, a world current system, a way of converting the XY pixel to RA and DEC, and also the photometric calibration for that. So basically the 0 point, photometric 0 point for that detector and that exposure. Let us take a quick look at this particular the image for this, and we'll look at the image, but we'll set the mask to be 100% transparent, so we don't see the mask at all. We just see the image. And this will pop up over here in the Firefly frame. And here you see it. Oh, wait, actually, okay. For some reason, sometimes it's a little bit tricky. It's actually all the blue. It's actually showing it's actually showing some of the mask information here. So actually, this is incorrect. It's actually showing the mask stuff on top of the other image, on top of the actual image. Basically the detection mask, and also we have a point that's crosshairs that indicate the center of the image. Other things of interest is you'll notice down at the bottom here, as you move your cursor around, you see the ARIA deck and the pixel value in data numbers. For instance, this was at 36.376686 data numbers. All right, continuing on, we wish to grab the back. As an example of how to manipulate an image before reprocessing, we'll use the butler to retrieve the sky background image, which was originally subtracted. So here the background sky has been subtracted, but we want to add that back in. So first we'll grab the background, and then we will plot it in a second window. And so here is the original image. This is the image after with the background subtracted. And here's the background, and so you see there's a kind of a gradient there. And now what we're going to do is we're going to add this background back into the original image, and that is what we would do for when we want to run source detection. So we'll add that, and then we will display it as a third option. And why don't we just move things around a little bit so we can see things better. So let's see, let's make this, and it is fairly big. All right, that's not allowing me. So if you make it really big, you can actually you'll see the data numbers in addition to the equatorial thing, but I can't make my display big enough. So what I'll do is a second thing that's described here is click on the expand readout icon, and so that's this, and we can move this over here, and you can move over a given image, and you see it, and you can also see in the lower part, you can see the value. So here is the background subtracted image, and they're all kind of scattered around plus or minus 100 data numbers. So it's the subtracted version. Over here we see the background, and you see it's roughly like 3.8 times 10 to the 3 data number, 3,800 3,800 data number units. And now if you look here, this is what we've added the background to the background subtracted image, and now here is what the image would be like with the background re-added, and you'll see that the values are around 3.8, 3.9 times 10 to the 3 data numbers. Okay, and this is, you close each frame by, well, let's see, finding the little X on the side and clicking it off. And now now we can kind of continue on. And why don't we just go ahead and delete those and move on. Okay, now we'll start now we'll actually do first of all, any questions so far? All right, let's continue on. Now let's actually get to the main part of this notebook. The source detection, deblending, and measurement. So the LST science pipelines source detection, deblending, and measurement tasks. We already imported those in the first cell. You can learn more about them at pipelines.lsc.io. So the schema, so we want to create a schema that describes the output properties that we measured for each source. The schema needs to be passed to all the tasks, each of which will add columns to it when it runs. So the first thing we want to do is create a minimal schema for a source table, the thing that contains all the detections. So we do that. There's not really a whole lot in there. There's a ID number, an RA, a DEC, and a ID for a parent source when the deblending goes through. We also want to create a container, which will be used to record metadata about the algorithm execution. So I'll run this. And here's a critical aspect. We need to configure each of the different tasks. So each task possesses an associated configuration class, and the properties of these configuration classes can be determined from the classes themselves. I actually won't go to. I won't actually. I'll leave it to the user to uncomment and look at these, because we do have a lot to go through in a relatively short period of time. But I'll just jump over here, and we're going to set the basic configuration parameters and then instantiate each task in turn. So the first task will be to characterize the general properties of the image. For instance, the plane spread function associated with the image. So what we're going to do, okay, you can choose how many iterations this task goes through in calculating the PSF. We're just going to set it to 1. I think the standard is like 3, but we'll set it to 1. So we create a config class. We'll set the those PSF iterations in the config to 1, and then we'll pass it to the characterize image task, which we'll assign to a variable name of char image task, and then we don't need the config anymore, so we'll delete it. All right, the second step is source detection. This detects individual sources. So what we will do here is, okay, the default LST for LST catalogs is basically a 5 sigma detection. We're going to change it to a 4 sigma detection. This detects slightly fainter sources than we normally detected in the main LST pipeline. So what we do is we create get to the config class for the source detection task. We set the threshold value to 4, and we'll set the configuration type to standard deviation. So this will be a 4 sigma detection threshold. And then we'll pass this this configuration to the source detection task, setting it to a variable with the name of source detection task. And then once again, you can delete the configuration because we don't need that anymore. Third, we wanted to blend the objects. So you may have objects that are close together, and you want to blend them to have separate the individual objects that are maybe overlapping objects. So we don't actually need to do anything special here. So it blends basically the source to blend task. It blends overlapping sources into a parent and child sources. But at least for this tutorial, we don't need to do anything special here. So we just send the schema, the minimal schema to the source detection task. And next, for the last the configuration steps is we'll measure the properties of the blended sources. And once again, no special configuration is needed here. So, but we can just take the configuration class and pass it the schema, the basic configuration, and recall we had that algorithm that variable which contains structures for the algorithm metadata, and we'll pass that to this also. And then finally, we'll create a table, a source table, which we'll call tab, using the minimal schema, and it will hold the output of the analysis from this following section. And then after we create the table, we no longer need that scheme, that minimal schema, so we can just delete that. And then we are, so then we'll finish configuring things. Now you may want to say, oh, oops, I made a mistake. I want to go back to three PSF iterations for the characterized image task. Well, you can't just change the parameter. You have to actually, after you create the task, to change it, you have to redefine it and then redefine the task. So for instance, if you want to go back to 3 iterations for PSF in the characterized image task, you need to do the config.psf iterations equals 3, and then recreate, then repass that to the characterized image task. All right, let's skip these next 2 things. And now we will retrieve a fresh version of the image that we grabbed it before. We'll grab a fresh version again. Now, one thing, this image, it's in its mask plane. It already shows where all the objects are already detected. But we want to redo this again. We want to redo this, so we need to clear the mask plane of anything that says this pixel has a detect object in it. So what we do here is we run the calyx mask remove and clear mask plane function and tell it to remove all detected, remove the detected flag for any pixels that have that. And now here we actually run the pipeline. All right, no, wait, do we? We'll see. Let's see. I think, let's see. Okay, first we'll characterize the image. We'll run the calyx image through this characterized image task, and okay, you see it's running. It's found 249 positive peaks at first, and then it trims things. It finds now there's 212, and it's okay. It's finished. So it's used this to calculate the PSF and other things about the general image, and it saves this in what's called a struct structure, which is just a generalized container. It's not so interesting but you can take at first, but you can take a look at it. You can see the construction of the structure as an exposure, a source catalog, a background, a PSL cell set, characterized class, and a background model. And you can actually even take a look at the result. It's not too interesting at first because there's lots of nans and lots of falses and so on. But we can show a way to interact with this is to choose a particular pixel and grab what the PSF is at that pixel location. So here we'll choose a pixel at x equals 1700 and a y equals 2100, and we'll use the elasticity.geom function to create a geometrical point, which can then later feed to another which we feed on to a function a little bit later on. We grab the PSF, then we calculate the sigma for using the determinant of the PSF function. We grab the pixel scale in arc seconds. And then so this will go to the sigma in pixels times pixel scale, and to convert sigma to 4th half maximum, you multiply by 2.355. and we'll print that out, and then we'll just delete that stuff. We don't need that information. So we see it, the PSF as a fourth half max of 0.97 arc seconds. Okay. Any questions at the moment? Okay. All right. Okay, thanks. Okay. The next step, we've characterized the image that's for these CalXP. Now we want to do the source detection step. So I'll run source detection, and we'll feed it the table, which is was empty, but won't be current, but will be filled, and the CalXP, and we'll send it to the source detection task. And okay, it detected 2,292 positive peaks and 108 negative peaks within a plus to minus 4 sigma level. And then, yeah, we get the 2,292 positive peaks. So with threshold value set to 4 sigma, over 2,000 sources are detected. We could have switched that around if you said say we had used a threshold value of 10, there would have been about 940 peaks detected. We know that's because we ran this before using a different level of the threshold. And yeah, you can do that, and you can do that too. Okay, we'll create a variable to hold the detected sources. And we'll just uncomment this out to quickly look at it. And we'll see, yeah, various sources. So far, not too much information about them. They're detected, and they'll be characterized more fully in the later steps. If you want, you can write that, write this to a fits table on in your home directory, but I'm going to skip that over myself. But you can comment those out and write those to a source directory. Okay, the next step is the source deblending and measurement. So we'll run the source deblend task and the single frame measurement task. All right, and so we did deblending. So we have now 2,500 sources, and then we'll measure the sources. And this will take a few seconds. All right. And then it's useful to make sure, it's useful in general to have your sources in a continuous sequential area of memory. So we'll make a copy of this, and we'll tell it to make sure that the data are all in the same area of memory using this copy step. And then if you want, you can take a quick look at it as an AstroPy table. And now you actually have values, RAs, DEX, and some other information. Oops, sorry about that. Okay, and then now let's take a quick look at the image. So we'll display it. We'll display a portion of it. We'll display we'll use a B box, and we'll plot up a small region of it of the sky of this image. I hope. Oh, that's a screen. Oh, I haven't actually plotted. Okay, sorry. We're in the bounding box, or the information for the bounding box, and then we'll create a cutout using a CalXP factory. So this is that's cut out of within the full CalXP. And now let's display it in Firefly. And here it is. And once again, yeah, it should be setting the transparency to 0, but actually it's show for the mask, but here it's the mask is overplotted. I'm not quite sure what's going on there. We can kind of increase the size here too. Okay, now we can also plot the detected sources. And so we see they're all detected. And then finally, we can delete that. Now I'll quickly go over, we're actually seeing these footprints here. So footprints basically are like S-extractor segmentation maps. They basically show which pixels are associated with detection or detected object or image or source detection. So we can grab I'll just very quickly go through this because I'm running low on time. I'd like to get to the next, to try to get some of the next section. So I'll kind of leave, actually, I'll just kind of skim over this and let the user look more closely at this. But you can actually take a plot, you can plot up what the mask, what the footprint looks like. And the mask actually has different values. I mentioned there's a detected value for each pixel, but there's also so these are bitwise masks. So the different masks are additive, and they don't. So you can add these up and get a number, and then unadd them up to get out whether it's a cosmic ray crosstalk, whether or not it's detected, detected negative, it's on the edge, interpolate, and so on. So I'll just kind of skip over this quickly because what I really would like to do the force photometry. So, okay, so the LSST pipelines have a task for force photometry called force measurement task. And here we'll use this task. We'll use the PSF image to measure flux. This task we use the PSF image to measure flux at any user supplied coordinates. It's not a fit though, so flux returned is returned whether an astronomical source is there or not. Force photometry can be very useful for including sources below the detection threshold or non-detections. But there are some issues you have to be aware of, and we'll try to cover that. So let us create a minimal schema again, like we did before. For the force measurement task, we need a few extra things for the columns of the schema. So you add to the minimal schema. I won't go into details here, just say that there's some important things to add there. And we'll also add a flag. 0 be for faint objects, subthreshold objects, and we'll also add some random off-source source currents. 1 for random off-source currents. We'll create a list of off-source currents too. So we'll add this field. Then we'll create an empty force source catalog using the schema. And of course, at first we'll have 0 rows because we haven't done anything yet. Then we'll configure the force measurement task. I won't go any details here, but basically this configures the force measurement task for you. And then we will we'll define the task, and then we can delete the configuration because we've already passed that on. Next, we'll define the coordinates that we want to measure. So in particular, we'll create a set of, let's see. So the scientific significance for force photometry include measurement of subthreshold or faint sources, or a need for an upper limit on the flux of a time-varying source. Now, the potential drawback of force photometry is that all the flux within the area of the PSF is included, which means that nearby sources can contaminate the force photometry. And we'll see this in section 5.4. For this example, we create a list of subthreshold or faint object, faint detection coordinates, and some random off-source coordinates, which are not near any detected source. We'll use a region within 2 arguments in the center of the field for this step. So first, we'll create a numpy arrays the right attention declination, XY pixel coherence, and instrumental flux and error from the list of detected sources. And these are sources that we detected in the earlier when we did the detection, the 4 sigma detection threshold. And then we'll use the bounding box in the WCS to get the central currents of the CalXP, convert the pixels to sky currents, and calculate offsets between the sources and the image center. And then we'll define the maximum offset from the image center to be 2 arc minutes in units of degrees. And we'll just we'll grab all the sources which are have sales noise between 4 sigma and 5, between 4 and 5. Basically, things that are fainter than the usual measurement, standard measurement, what we measured earlier within that central region. And then we'll define new arrays to hold only the information of the sources to be used for switch photometry, and then we'll clean up. I mean, I'm kind of running out of time, so I don't go into the detail of these particular code cells. I'll just kind of run through them. So here we detect all the things which are between 4 and 5 sigma detection threshold. Then we'll add the coordinates. Sky coordinates should be in radians in this case. We've added, so we have 32 of them. And then likewise, we'll create 32 random coordinates in the center region of the image and ensure they're offset by at least 40 pixels from the nearest detected source. So once again, I'm not going to go through the details of this code cell. That's going to run it. And then we'll use the images WCS convert those pixels from those random objects, those random pixels, the sky coordinates. And then we'll add these random off-source coordinates to the source catalog. So now we have 64. Oh yeah, we've doubled the number of objects that we want to use. Now I'll run the task. First, we create an empty catalog to store the first measurements. Then we run the first measurement task. And then we'll explore the results. So look at the first measurement catalog as an AstroPy table. We'll add the type flag column from the first source to this table. We'll take a quick look at the table. Let's see, yeah, we have all this information now. Now we'll display it. We'll display this in the frame 1 in the Firefly window. So run that. And here we are. We have that that area. Now I'll overplot the currents used for the first photometry on the image. We'll use circles to mark the faint sources. Those be orange, and the random off source will be in cyan, showing where the location of the first photometry was done. So here we see those. Oh, these are the mass is kind of showing up here. I think these are lead trails or something. You can just sort of ignore that for the moment, but we can zoom in by using your mouse scroll bar, and you'll see the remember the orange are the faint objects that we detected, and the circles are just random objects. Okay, we zoomed in. Now we can compare the first photometry for those faint objects with the measurement we did in the earlier with the standard setup earlier. And we see the detection threat. It's basically 1-to-1, but there are a few outliers. So this shows the original flux detection from the section 3. I think that's section 3. And plotted against that is the PSF flux from the first photometry for this original 32 sources that were originally detected. Now, sometimes you'll have there'll be contamination from nearby objects. For instance, like here, if you zoom in, if you look at the sky here, there's a galaxy nearby, so it's kind of probably causing some excess brightness there. But let's see. Okay, we're going to replot this, but now we'll change. We'll color yellow as any of the ones that had flux excess greater than 20 counts. Okay, so here you definitely have one that so definitely these have kind of additional things in the background. And then finally, why don't as a final exploration, we'll look at we'll plot the histogram of the force flux PSF fluxes for the faint objects and also for the random off-source coordinate, for the objects that were doing the force photometry of the random coordinates, the cyan pointings here. And what you'll notice is that the things that were faint, they all have a force flux which is non-zero, definitely non-zero. But the random things are kind of scattered about zero, which is what you'd expect. And that is it. Any questions? Anyone still there?
Yeah, everybody's still here.
Okay. Were there any questions in the Slack channel?
I didn't see anything in Slack channel. I was monitoring this. There were some questions about difference between CalExp and COAD, but I think Jeff answered all those in the chat.
There's a question now from Gideon on, can I explain what a schema is one more time? I can give it a try. It's basically a structure for containing, let me hunt that down here. Let's search for where schema first pops up. Okay. Oh, all right. So it's basically a structure that contains information for the output properties that from the detection for all the sources. And I'm not sure. Maybe Jeff, is there anything you'd add to that? Do you think?
I mean, yeah, I think that's a fine description. It's basically it tells you what each of the columns in a database contain. So so it should, at a minimum, it should have each column should have a name and a description, so you can see the thing. This is like position, and RA-Dec describes what's in it. They should all have units as well, but sometimes they don't.
In general, from a database perspective, the schema describes how the tables and their formatting and so on. And in this case, in this particular case for LST, it's basically a spot for the output of the pipeline is basically a spot for the output it's the structure that we stick the pipeline tasks stick the results in for the source detections and measurements. But more generally, it's a database concept for defining how the columns and what the names the types of data in those columns and so on. Oh, thanks, Jeff. You put in the chat the schemas for all the tables in DP0.
All right, I don't see any more questions in chat or on Zoom. So I think at this point we can probably thank Doug, and we can move on to Jeff Carlin. Jeff, I think that you maybe, for the benefit of everybody who joined in late, maybe you can just say a couple of words, or maybe I can show, or since you're going to be speaking, maybe you can say what people need to know, because it's a custom notebook.
Yeah, I'll definitely show people how to access the notebook that they will need, because this notebook, as Greg was alluding to, this notebook isn't automatically loaded in your science platform instance. So hello everybody. We are going to talk about light curves of variable and transient sources. So to get right into it, we'll go to the science platform page and we will open the notebook aspect. And as you'll usually want to do, you pick the recommended image and medium container, and this should just take a second to open. And then while that's opening, let's see here. I'm gonna grab this link. Okay. So, and then the link that you'll need to visit, I just am pasting into the meeting chat. Okay, we're getting there. Okay. So what you'll need to do is open a terminal. So click the button that says terminal. And then here, if you type CD and then a tilde, sorry, that will take you to your home directory. So that was here. Sorry, it keeps wanting to spell check me. It's not helpful. Anyway, you do that, and now you're in your home directory, and now we're going to make a directory to put things in. So I'm just going to call it temp here. So like that. Okay, and then that link that I gave you, you want to, the next thing first off, you want to change to that directory. So change CD is directory. Okay. And then the link that you'll need, I sent you this delegate contributions repository. If you go to the green button that says code and make sure you select the HTTP version, and then just copy that URL to your clipboard. So you just need to copy that, and then you go back to your science platform, and then you type git clone, and then paste in that link. And when you execute that, it will download that entire delegate contributions repository to your temporary directory that you created. So that command that I just issued I just pasted that into the chat as well. So now you'll see if I list what's here, that delegate contributions DP02 is here. So now I can go and open the notebook that we want by opening this file browser. And I go to my home directory, and remember we put it in temp, capital temp. And so I'll open that folder, and then it's delegate contributions DP02. And the one that you want is in Data Academy time domain. So it's in that folder, and you see it's 07C light curves. And if I double click on that, it should open up the notebook. Let us know if you're having trouble getting that. I'll pause and make sure everyone is able to get to that. I just realized that this was checked in fully executed, so I'm gonna I'm going to do something. You don't have to do this, but you can if you want. I'm going to restart the kernel and clear all of the outputs so that it doesn't give away all the secrets before we execute cells. But so now, yeah, now it's not executed. Okay, so hopefully everybody's been able to keep up there. Actually, here, let me zoom a little bit so you can read things better. All right, so this is basically a combination of two of our tutorial notebooks that are in your tutorial notebooks folder. There's notebook 7A and notebook 7B, which are 7A is looking at supernovae and light curves of supernovae, and 7B is looking at light curves of variable stars. And so this is kind of just a combination of both of those that Vincenzo Petrarca has created for this Data Academy. So what we're going to do is we're going to use the TAP service, the Table Access Protocol, TAP, to query various time domain data products. And then we're going to plot light curves of stars and supernovae. And you'll see that it involves joining various different tables to get the information that we need. And then if we have time, we can actually do some science analysis on these objects, but we cannot get to that. So as usual, we start by just importing all the packages we need. And in fact, for this, most of what we need is just NumPy, matplotlib plotting, and then a few AstroPy things, including, sky coordinates and the units. And then the only specific Rubin thing that we need is the get tap service. So we'll execute that. And then we set up some plotting defaults just to make the plots look nice. Okay, and then these are just a convenience for this notebook. We set up these. We set up this list here of all of the filters. So this has UGRIZY in a list that we can use for labeling plots. But you'll see we also use it to help us pick out measurements in each of the filters later. And then for just to make it easier later on, we define colors corresponding to each of the filters and symbols for the plots that we'll use. And so we'll go ahead and execute that, and we won't use those for a little bit. And in order to actually calculate, proper distances to supernovae that are at cosmological distances, you need to actually define a cosmology. So that's what this is doing here. We don't talk much about that. And then as we do in many of the notebooks, when you want to access catalogs, you initialize the tap service by doing this get tap service. And this tap endpoint is the DP 0.2 data set. So that's all the preliminary stuff. So now we get to do the fun stuff. This section, we're going to look at a star that we remember the data preview 0.2 data set is a simulated data set. So we know the truth of what was simulated. In this case, we're going to start with an object that we know is an R-Lyrae variable star. R-Lyrae stars are pulsate variable stars. They actually pulsate, they grow, the radius will double and contract back down over the course of a few hours. And that, of course, means that they get fainter and brighter as they're pulsating. So we're going to look at a light curve of one of those. And since we know the truth, we know exactly where it's located in RA and DEC. So we'll just create a variable for the RA and DEC positions. And then the first thing we want to do is find this star's entry in the object table. So remember, the object table is the measurements from the co-added images. So there should be one entry for each object. So you'll see here, we use, we say select these columns. We want RA DEC, some fluxes, a couple of flags, and we want to convert some of the fluxes to magnitude. So this is a function that does that for you. And we want the extendedness values. And then we say select those from the object table. And then we want only objects that are contained in a circle around that position that we defined up here in RA and DEC within 0.001 degrees. So there shouldn't be very many objects that close to that position. And we want to set the flag that typically gives you non-duplicate, good quality measurements. And then this just sets up the search, and then this executes it and returns it to a table. And it should just take a very short time. And then if we look at that, you see what we got back was a table of length 1. So we got our one object at the position that we requested. And the main reason we needed that is because we need this object ID. Because this is the object ID that is used to do forced source photometry. And you can also note, if you look at the table, the extendedness flags, for example, they all say 0, which means false, meaning it's not extended, which is good because we're looking for a star. You can see that the magnitudes are all around 18th magnitude, so it's a bright star, so we should be able to detect and measure it very easily. Okay, so as I said, we use this object ID to identify it in the forced source table. So remember, the forced source table is taking every object from the object table, going to its position in all of the individual visit images, and forcing the pipelines to measure the flux at that position. And so the key that ties these two tables together is the object ID. So we just extract that object ID from that table into a variable. And then we're going to do another tap query. And you can see this one, we add one extra bit to it, where we do, as always, you do select and you tell it the columns that you want. And we're going to select, coordinates, fluxes, magnitudes, from the forced source table, and we call that SRC source. And then you see we're going to join that table on this other table known as CCD visit. And we need that because the information about the time that each image was taken resides in this CCD visit table. And so that one's called viz info here. And so you'll see that the CCD visit ID exists in both tables. So you can join on that value. So this will pick the corresponding entries from those tables. And then we say where the object ID equals the ID for the star that we identified. Okay, so then when you extract the results of that into a table, the length of that table is 432 rows long. And so this is telling us we have 432 measurements of that particular star. And you can see what that table looks like. Here are your 432 measurements. Notice that the coordinate is the same for everyone because that's how the forced photometry is done, and the object ID is the same for everyone. So we know this is all one particular object. And now we have all of the magnitudes measured in each individual visit. And you can see a little further over. Oops. Sorry. If I slide like this, and you can see we have this exposure midpoint MJD. So that's the modified Julian date of when each exposure was taken. And finally, note that the first column you see here is band, and you can see that more than one band is included. So this gives us the measurements from all of the bands. So here you can see the R and the I. So we'll pick them out from each band separately in the next section. I'll pause just to see if there are any questions so far. Looks like we're good. Okay, so here we're going to do something. We'll do this kind of throughout the rest of the notebook. So we have all the bands in one catalog. This is just a way of flagging the measurements from each band, so it's easier to plot them or to, work with those arrays. And so this is just creating a dictionary, this pick dictionary. It's just empty. And then remember, we defined that list of the plot labels, UGRIZY. So we just say for each one of those labels, set this dictionary entry for that particular filter to a flag telling us whether the band of each row equals that filter. Make a little more sense if I just execute it and show you what it looks like. So you can, sorry, my mouse is dying. There we go. So you can see that if I say and then give it a key U, that will get me this array of true false values, meaning that the rows that are set to true have a U band measurement, the ones that are set to false do not. And you can see there's UGRIZY in this array. So that's kind of just a convenience, so that now, for example, if we want to plot the R band light curve, all we have to do is from that sources table that we had, just sub-select from it using pick and then the key R. And then we'll just plot the time of observation and the PSF magnitude. And this should be a light curve. And there you have it. And so you can see a light curve of remember the simulated DP 0.2 data set span is a roughly 5-year simulation. So this spans about 5 years of time. And you can see that this star is definitely not the same magnitude in every measurement. It is bouncing all over the place. So you can guess that it's a variable, but what type of variable is hard to know. So step one, we can say this is probably a variable. That's great. So now we want to move on to actually figuring out what type of variable is it, and can we see what its pulsation cycle looks like. So in this part, we get to do a little bit of science. And so that's basically called, once you identify the period of its pulsation, you can put each measurement into phase. So we're going to create a phased light curve. So a common way to do this is to use this thing called a Loam-Scargill periodogram. The link to the AstroPi version of that is given here. It'll take you to this. And it's basically a statistical tool that identifies periodic signals, if there are any, in a time series data set. And you can read more about it here and in the original paper by Loam and Scargill. So we'll use that pretty much out of the box from AstroPi to find the best period and then fold the light curve onto that phased period. So again, we do a similar thing to what we did before, just to make it easier. We're going to pick out the times in MJD and the magnitudes in the same way we did before. And one additional thing we have to do here is we need to tell that Loam-Scargill routine from AstroPi that this is in units of days. So this is using the AstroPi units days. So we've extracted the things we're gonna use, and then we're gonna set some limits, because the Loam-Scargill periodogram by default will just search over any possible frequency, but we know the properties of our Lyrae variable stars. We know that they have periods less than a day. So we'll search basically from 0.05 days to 1.05 days. We'll set those as the limits, but actually the periodogram is doing everything in frequency space. So we do 1 over the periods to get the frequency limits for those. Okay, and then we're just going to run this without setting anything fancy. This Lomskargel, you give it the time of observation in MJD and magnitudes, and we just set the limits, the minimum and maximum frequency values that we defined above, and it will return to you a list of frequencies and powers. And basically, you look for the place where the power is maximized, and then that frequency should correspond to the periodic frequency of the star. So we're just going to run that without any fancy settings or anything. And because these are really nice simulated data, this, of course, is going to peak at a very specific frequency, and it's going to look really nice. So this one, I won't explain this in detail, but this is just basically picking out the peak frequency, the highest power from for each of the bands. And so that here, you can see we find the frequency for UGRIZY, and it looks almost the same for all of them, which is a good thing. And that corresponds to a mean period of about half a day. And so to see what that Lomskargel periodogram looks like, we can plot the power versus frequency that it returned to us. And you can see here, if I plot that here, in the left, this is the frequency, and this is power on the vertical axis. And you can see that one peak is much taller than the others. And we've marked it here in red for convenience. And then if you convert that to period, remember just inverting that, you can convert that to period, and you can see here's the period of about half a day. And that's by far the largest peak. So I think we found the right period. Okay, so then we want to use that period to actually put all of the 432 measurements we had into the pulsational cycle of the star. So we picked out that best period, this half a day-ish period. So we'll just define that as a variable. And then what this does here is we just take an arbitrary point, and what we take is the very first measurement in the G band, and we say that is time equals 0. That's the beginning, the starting time. That's totally arbitrary. You could take any time as a starting point. And then the second thing that we do here is we just say, okay, how many periods have elapsed? And so that's what this line here is doing. You say, take the time of the current observation minus the T0 that we set, and then divide by the period, and that will tell you how many periods have elapsed. But of course, we don't actually want to know that it was 2.75 periods. What we really want is just the 0.75 part. We want to know where are we in that cycle. And so that's what the second part does, is it picks out the phase by just using the modulus function and dropping the 2 full periods and keeping only the 0.75 in the example. And that should then give you phase for every one of the measurements. And hopefully, if we plot magnitude versus phase, it will look like a very nice coherent light curve of a variable star. And so that's all this does here. And you can see, again, we're looping over all of the filters to plot a separate light curve for each filter. So we just plot phase and magnitude, and hopefully, if we've done everything right, they will look like nice light curves. And indeed, they do. They look like a very nice R Lyrae star light curve, where it increases to this sharply to this bright peak, and then gradually fades. And then, of course, this would repeat. And you can see that the shape kind of differs in each of the different bands. You can see that by plotting them all together on top of each other instead of here we offset them. But if we plot them on top of each other, you can see the amplitude is higher in some bands, like the G and the U. And you can see that you can tell that the color is changing during the phase because the relative change in magnitude is changing here. So yeah, it looks like an R Larry star. That's fantastic. Now you could imagine going and doing something like that for all of the potential variable stars in the survey. And so before we go on to a supernova, I'm going to pause and see if anyone has any questions. Dude, also, I forget when I'm done. I go till 8:30. Yeah. Good.
Nothing in chat, and I don't see anything in Zoom in Slack channel.
Okay, great. Well, we'll move on then. So now we're going to do a very similar activity, but for a transient source, you know, a sort of a short time period object that brightens and then fades again. In this case, a supernova. And in this case, again, we're going to use the fact that we have the truth information because it's a simulated data set. We're actually going to go to the truth table itself and do some selections to pick candidate objects. In particular, so that again, we do select these columns from the truth summary table within, this is saying within half a degree of this coordinate in RA and DEC. And then you see here that we're going to say is variable equals 1, meaning that it's been identified as, or it truly was simulated as a variable. 1 means true. The truth type equals 3. That is the code for supernova in the simulations. And because, again, it's the truth table, we know the redshift, so we can say, let's pick redshift less than 0.3 because then it'll be bright enough that we get lots of measurements. And so we'll execute that query. And in this case, just to show you a different way of looking at it, we extract it to a pandas data frame instead of an AstroPy table. So that's what that looks like as a data frame. So you see we get the RA deck and then the ID of each one, the host galaxy, and the redshift. And this is a list of 30 objects satisfying those constraints. So here we're just going to select one of those. In this case, it's this one in the line 22. And we're just going to use its ID to find it, or to find its coordinates, and then use those coordinates to do a similar query to what we did for the R Lyra star. So this just says from the data frame, pick out the location, the row, essentially, where that is the ID. And then this one says, now pick out the RA value and the DEC value and put them in an AstroPy sky coord object for that row. So that supernova that we're going to look at. And now we're going to do exactly what we did for the variable star. We're going to go to the object table with that position, and so that we can get the object ID. So that's this. And again, you can see because we used a very tiny radius, we only get one object back. And then we extract this object ID, and then we go to the forced source table to build the light curve. And again, we do the same join that we did last time, where we join it to the CCD visit table to get the time of observation as well. And then we extract that, and you can see we have 428 measurements of this one object. And again, we do the exact same thing we did before, where we pick the different filters measurements. And then here is what the light curve for that in the R band looks like. So again, this is over more than 5 years. And you can see most of the time at that position on the sky, there's basically nothing. I think this is essentially the background level that's being measured at 26th magnitude. But then you can see here for a span of about 100 days, there's this peak. There are few measurements that go all the way up to 22nd magnitude. That I think is our supernova. So because most of the rest of this is not very useful to us, we're just going to zoom in on that roughly 100 days around that. And we're going to do that looking at the DIA products. The DIA is difference image analysis. This is where we take, when we take a new visit on the sky, we take a template image of that same piece of the sky, and we scale it properly and subtract it off of the new image. And if some transient has appeared, there should be some residuals when you do that subtraction. And so that's what we're going to look at. And again, just like we have for the direct images, we have from the difference images, we have DIA object table, which is the sort of set of all of the unique objects. And then we have the DIA source table, which is all of the individual measurements. And then, of course, the forced source on the DIA object table is another one. So we'll look at those for this transient object, which we think is a supernova. So just like we did before, we're going to do the same thing again, where we find the object, this time in the DIA object table instead of the object table, so that we can get its ID. And again, hopefully that just brought us back one object, indeed. And then we get its ID. And now we, just like we did before, but instead of using the source table, we'll use the DIA source table. And in this case, the DIA source table actually already has the midpoint of the observation, so we don't have to do that join with the CCD visit table. And you can see here, there are also two different types of flux. There's this PS flux and there's tote flux. So the PS flux is the PSF flux as measured on the difference image. And then the tote flux is the PSF flux measured on the direct image without the template subtracted. So we'll extract both of those. So we have the difference magnitude and the direct image magnitude. Okay, and then we do the exact same thing we did before to pick out all the separate bands, and then we're just going to plot those all on a single plot. And so again, this is just plotting the midpoint of the observation and the magnitude. And so here we are. This is our multi-band light curve. And now you can see we've zoomed in so that we're only looking at about 200 days instead of 5 years of time. And you can see that because the DIA source table only has entries when there's a source that's detected in the difference image, that you don't get all of those at 26 magnitude. Those just become zeros in the difference image. And so you actually get a very nice clean measurement of this supernova rising to a peak, about 3 magnitude rise, and then gradually fading. That was in the DIA source table. But of course, if you wanted to see every possible image this supernova could have appeared in, the DIA source catalog won't get you there because it only has things that were above 5 sigma detection in the difference image. So instead, you can go to the forced source on the DIA object table, which is analogous to the forced source measurements in the direct images. But in this case, sometimes you can force it to do a measurement and it's going to measure 0 flux. But that's informative. So we're going to do that in the same way we did before. And again, this time you do have to match to the CCD visit table. And then we will plot the light curve again. Okay. And now you see you get a big mess, but that's because this has a measurement on every one of the 428 images that overlap this position of the sky. And so again, you can see that most of these are probably, essentially zero flux. And then you have this time where the supernova is near its peak over a couple hundred days. And so we can zoom in on that portion just to see what that looks like in forced source measurements. And again, now you can see the supernova rising from very faint, basically no flux there, rising by many magnitudes and then gradually fading. And actually, and I think the timing wise, that works perfectly. So that shows you how to extract and look at the light curves of different types of objects. And, some of the details of how you do things like, joining the tables to get the information that's contained in various tables. And then the rest of this notebook goes through some more, it's more like science exploration of, okay, what if I didn't already know that there was a supernova there, or I didn't know there was a variable star there? How could we go about finding them from the catalogs? And that's what section 4 and 5 do. So section 4, we take sort of what we know about supernovae and how bright they should be, and what the shape of their light curve should be. And we apply some of that to set up a bunch of sort of criteria, and then apply those criteria in the, sorry. Okay, I don't know why it's doing that. Apply those criteria in the query to get a list of potential supernovae. And then a few more calculations to sort of get a list, and then, I should execute. Well, no, I won't execute it. We can do that in a breakout. But basically then, and then you can plot things that are returned and say, does this look like a supernova light curve? And then in section 5, we're going to do similar, but figure out ways to extract candidate RO Lyrae stars from the catalogs based on what we know about their pulsation properties and the brightness and some measurements of the variability of objects. And so that's what this last section does. And it selects some candidates and plots them, and does the periodogram to get the periods for them. And so if we like, we can go through those sections either. Of course, you can always go through them on your own time, and we could look at those in the breakout if we have a chance. And I will pause there.
I don't see any questions or comments in either the Zoom chat window or in the Slack channel, so I think that we're all good here. So I think maybe at this point, we all should take a little break and maybe spend another 20 minutes after a break, maybe just going through some of the details and questions and answers into breakout rooms, if that's okay with all of you. Yeah, okay. So while you're getting your coffee, tea, or I don't know what else for those who are in the end of their days, I will set up some breakout rooms, but I will stay in the main room just in case if there are any specific questions. And I think that it's probably just the 3 of us today on the call from the community science team. So I think that I will set up 4 rooms just in case if there's anybody who wants to work with another person from their own institution, maybe in a breakout room. All right, so I will see you. It's 8:30, perfect timing, Jeff. And we're gonna reconvene here in, do we need more than 5 minutes, you think?
I'm okay with 5 minutes.
Yeah, let's
5 minutes is probably sufficient.
Yeah, let's just do 5 minutes. And so it's 8:31 now, so let's do it 8:36. All right, I opened the breakout rooms. I will stay in the main room. I know that there is one room for Douglas and one room for Jeff, and bring your questions and whatever concerns you have or clarifications. Hi, Youngmin and Wang Shu. If you want to listen to whatever is going on in any of the breakout rooms, feel free to join. I can be here by myself. Or if you have any questions for me, that's fine too.